This topic is bias variance dilemma, and we'll begin with a MATLAB demo. So I want to fit a polynomial to sinusoidal data. So I have y equals 5 sine pi over 2x. This is the curve, and x ranges from 0 to 4. And I create 15 samples from this data. So this is the curve, the red line, and the blue points are 15 random samples. And then I'll add noise to those samples, which I'll use for training. These are the training samples with the noise. Next, I'll fit a polynomial of degree n to the training samples. This is an example of a polynomial fit. The solid red line is the polynomial fit of degree 4, so it's a biquadratic polynomial, and the dotted red lines show the actual sine wave, and it looks like a pretty decent fit for n equals 4. And then I'll vary the degree of the polynomial n, and each time I will keep track of how well the polynomial fits the training samples and how well the polynomial fits the original sinusoid. And these two errors will be the training error and the true error. The training error is how well the polynomial fits the training samples, and the true error will be how well the polynomial fits the sinusoidal plot. This is a first order polynomial fit. First order polynomial being just a straight line, you can see that this is hardly any fit. This is a second order polynomial that is a parabola, and this again doesn't fare so well. What about degree 3? So this is degree 3, and it does fit the data quite well, and it looks like a sinusoid. This is an even better fit. It's a degree 4 polynomial. Now degree 5, let's keep increasing the degree of the polynomial. Degree 6, degree 7, it begins to look less like a sinusoid at this stage. It fits the data even better. As you can see, it cleanly fits all these points and most of these points except probably this one here, but on the whole it doesn't look like a sinusoid. 8, 9, it begins to look really crazy. It fits the data perfectly well, but doesn't look anywhere like a sinusoid. Degree 10, even crazier, 11, 12, so it looks really crazy when we increase the degree of the polynomial beyond a certain stage. Although the data is being fitted is very good. This is probably the only one that it didn't touch. Otherwise, this is a degree 12 polynomial. It fits the data perfectly well, but it doesn't look like a sinusoid at all. So what's going on here? This plot shows the plot of the error, the log error actually on the y-axis as we increase the degree of the polynomial from degree 1 to degree 12. The training error keeps going down as we increase the degree of the polynomial. But the true error, that's a reflection of how closely the polynomial fit behaves like a sinusoid, looks like a sinusoid, that goes down, but after a while it goes up back again. So the true error doesn't always decrease with increase in the degree of the polynomial. It goes down for a while and then it starts rising back up. This is for 20 runs of the same experiment with different randomization. And in all cases, the blue is the error with respect to the training samples, and that steadily goes down. But the true error goes down and then rises back up, and it goes really high for very high order polynomials. This phenomenon is known as the bias variance dilemma, and that's faced by machine learning researchers and practitioners of machine learning. So what's the right balance? What's the optimal model that one should pick to fit the data? That's the bias variance dilemma. Let's look at it more closely. So this is a schematic showing what we just saw experimentally. So the dotted blue line here is the training error, and the training error keeps going down as we increase the degree of the polynomial. This is the y-axis is the square error, and the true error goes down, and then after a while it goes back up. The true error goes down and then it goes back up. And so let's delve further. We also know that we had noise. If we remove the noise, then both those curves would move downwards like this. This is the training error without the noise here, and this is the error, the true error without the noise. And the same shape, but they just move downwards. So we have isolated noise as one of the components that gives rise to the error. What is noise? Noise is the intrinsic error in the data. And so it contributes equally to the training error and the test error, and it's not influenced by the polynomial degree. It's steady because it's intrinsic to the data, it has nothing to do with the degree of the polynomial. This is the same figure, and the difference is I have changed the terminology a little bit. I've made it more general. Risk. The y-axis, instead of calling it the error or squared error rather, I call it the risk. And the risk is defined as the expected error, which in this case is the squared error. It might not be squared error in all cases. It might be the absolute value of the error, but the expected error is called the risk. And the empirical risk is the risk seen during the training process. So one assumes during training a machine learning model that the samples reflect faithfully the real world data. And therefore one assumes that the risk one sees during the training is a true reflection of the real risk with actual data, but that's not always the case. So this is called empirical risk. This is the noise. The empirical risk is what we call the error due to training samples. And this is the true error. Now we call it the true risk. The x-axis, instead of the polynomial degree, now I'm making it more general. I call it the model complexity, because the higher the degree of the polynomial, the more complex the model becomes. We already saw that when the noise is removed, the risk from the training samples was steadily going down like this. And now we call this component of the risk the bias. Now, why does the bias go down like this? It's because the model, or in our specific case, the degree of the polynomial, when it was becoming larger and larger, it provided more flexibility to the model to fit the curve. And so to fit the curve, both the sinusoid and the samples. So as the model complexity increases, you see that this risk, now called bias squared, actually, square of the bias, this bias goes down. The model bias is the risk due to an inherent limitation in the model. So this bias steadily goes down as the model complexity increases, because the model becomes more and more flexible. It becomes less and less restricted. And when the bias is added to the noise, we get the empirical risk, which is the risk that was experienced during the training process. So the empirical risk contains both the bias and the noise. And the empirical risk keeps going down as you increase the model complexity. So one would think that the more complex the model, the better it will fit the training sample, so that's great. Let's keep increasing the complexity of the model. But we already know that that's not always the case. And so that's why we have the true risk. So this is the true risk. The true risk is when you deploy the model in real life with real data, with theoretically infinite samples. The risk would be like this curve here. It would still go down as you increase the model complexity, because a straight line can hardly fit anything. That was the degree 1 polynomial. A parabola could hardly fit anything, but then we increased to 3, 4, 5 the model complexity. Then it started fitting both the training data better, and it also started looking more like a sinusoid. But after a while, you saw a lot of squiggles appeared in the fit, and it looked less and less like a sinusoid. It was still closer and closer to the samples, noisy samples. So this was, the empirical risk was still decreasing, but the true risk was started going up, and it actually really went up after a while. So there is some other component. So we've taken care of the bias, which is the limitation in the model, and the noise is something inherent to the data, and we have no control over that. And there is yet another factor at play here, and that is what we need to know. So why is the true risk more than the empirical risk, and why is the true risk going up after a while? That's because of this third component called the variance. The variance here is the risk due to model sensitivity to sample set. So the samples is random sampling of the actual domain of inputs. So, and it's small, and of course it will be noisy, but mainly because it's just a finite set of samples, right? So the finite set of samples will provide only limited information about what's really out there. And so what happens is, if the model complexity keeps increasing, then the model becomes very sensitive to all these quirks present in the sample set. The small size of the sample set begins to play a role. The model tries to not only fit globally the samples, but it tries to look at the small details of the sample set, and those are quirks due to random drawing of the samples, and that's not reflective of the actual input data space, but the model begins to imitate those. And that's why this component, the variance of the model, begins to rise after a while when we increase the model complexity. So this is a fundamental equation. Risk equals bias squared plus variance plus noise. And the noise is something that we cannot help. And what we can help is the bias squared and the variance. As we increase the model complexity, the bias steadily goes down and down and down. Unfortunately, as we increase the model complexity, the variance begins to go up. And so that poses a dilemma. What's the appropriate model for a particular task? So this figure shows that. So this is the model complexity along the x-axis, and this is the risk along the y-axis. The noise is constant. It's inherent to the data samples. Bias squared, the bias is steadily decreasing. As the model complexity increases, the variance increases, and initially by a small amount, but then it shoots up as we further increase the model complexity. And then the total risk, which is because of the noise squared, the bias squared, and the variance, is this curve. It goes down and down and down, and then after a while it starts going up. And so this is the optimal point. One needs to have a model only as complex as this. Not a really simple model, but not a complex model either, because both will work equally badly. This illustration shows we have two-dimensional data, and we have points belonging to two classes, the red points and the yellow points here, and we want to separate out the red points from the yellow points. So this is typically binary classification. Really simple model would be like this straight line, this purple straight line here, and it won't do a very great job because you can see that it leaves a lot of the reds on this side and some yellows on this side too. So it doesn't do a really good job. On the other extreme is a very complex model. That's this red curve here, and that adjusts through all the nuances of the training samples, and that does pretty well with respect to training samples, but of course we now know that it's not really all that great. The optimal is the green one. It has some error in it. So you see one one yellow dot on this side and one red dot on this side of this green line, but overall the green classifier is the optimal classifier in this case. This is the same thing for regression, and this is not model complexity anymore along the x-axis. It's some x, and this is f of x. And so we have regression samples, these red dots, and the simple model is the purple line. It doesn't do a good job. It tries to fit a straight line to this data, which obviously is not a straight line. And the complex model tries to overfit, fits all these nuances in the training samples, and that's because we randomly generated and drew samples of the actual regression, and they also have their own inherent noise. The optimal model is the green one, and it's smooth enough, but it does overall match the data. So the whole idea is you need a model of optimal complexity. And that's the whole idea of the bias variance dilemma. How do you strike the right balance between the bias and the variance and select the optimal model for any particular task? The end.